So good morning, everybody, and welcome. It's glad to see you, everybody. So Jonathan wanted to start with a demonstration today, which is very cool. So basically, we're going to talk about friction a lot today, and in particular, I'm going to start by talking about kinetic friction. And what kinetic friction does is it will convert sort of kinetic energy into internal energy or thermal energy. The book calls it internal energy, but there's a way. You have your infrared camera with you? Do you want to turn it on?
Yeah, absolutely.
There's a way to actually see this thermal energy. He's brought an infrared camera, so you can see me sort of looking there in the infrared. A little bit of a delay, and then where do I want to? Are these the blocks? They're over here, right? Are you ready? I feel like they're not aimed right, but I'll pull it this way. No. Oh, you sort of see it? There's a little bit of like... The floor is somewhat heating up. Maybe I could do it with my foot. Look at that. It's all red. So that's where the energy is going. When you drag something along, you're putting all this energy in there, and you're actually heating up the floor. And so we're going to talk more about conservation of energy when we get to chapter 6. But that's kind of part of the idea of kinetic friction. So thanks very much. That's a really cool demo. All right. Okay. Very orange, too. Okay. Quick announcement. For next week's practical, Monday through Friday, I actually want you to bring an aid sheet because you're going to be doing a 15-minute mock quiz. It's just for participation only. You're going to be sort of self-grading it. And it's going to be based on will probably be chapter 4, actually, stuff we've been doing. So same sort of thing. It's kind of a good idea maybe to get ready with this aid sheet and have the same one you're going to bring to October 10th test, which will be on chapters 2, 3, and 4. So try to write the equations down from the summaries of these chapters that you might need. I should also bring, calculator. I guess you're allowed all the things that you're allowed during the test, you'll be allowed during this mock quiz. So, and you can read a little bit in the prep materials about what's going to happen next week. There's no experiment next week. It's more like practicing on problems and getting yourself ready for term test 1. I have also posted the marks for the mini term test, which was on Tuesday. A lot of you wrote it. Not everybody, but most people, about 90% of you wrote it. Average was 68%. There's the sort of histogram. Basically, around half of you kind of were 5, 6, 7, and the other half sort of 0 through 5. 125 students got 7 out of 7, so that's good. If you didn't write it, you do get a 0 on it, but question was, can I make up for it in the term tests? And the answer is absolutely yes. So if you look at the rules of the course, the syllabus, the mini term test is worth 5% of your mark in the course. However, your mark in the mini test will automatically be replaced with the highest of the other 3 tests that are in this course, the 2 term tests and the final exam, if any of these is higher. There was a question about this term test 1 that's coming up. Basically, it'll be, it's the format, I guess, so I'll have 10 multiple choice, and I think at least 4 of them won't involve any numbers. It'll be more conceptual questions. Plus 1 written question, like we're going to be practicing in practicals next week. And like you'll also practice on problem set 3, I think. And you'll have 80 minutes. So I think there'll hopefully be a lot more time and you won't feel as rushed. It is not my intention to make you feel rushed on these tests, quite the opposite. I'd like you to feel like you have lots of time. I want to test your skills at problem solving. not test your speed at problem solving. And then part marks, yeah. So the whole point of the written problem is that unlike a multiple choice question, you can get part marks. And so, in fact, I think it's out of 8 points, and the first 6 are just kind of all the different steps of setting up a solution that you'd need. And then the last 2 points are for actually solving it, the last equations and getting the numerical answer. So there's lots of room for partial credit, and it'll be marked by a human being, a PhD in physics who's looking down and reading what you do. So. Okay. This was a little disturbing. I got this, had a physics nightmare. Hot air balloon, instead of rising, was falling down at 9.8 down a window. And then there was a big crash and a big boom, boom explosion when it finally hit the ground and collided with a physicist. This is a dream, by the way, that was supposedly sitting on the second floor, who was somehow down on the ground for some reason. Then, a couple of seconds later, all the little bits from the crash and the destroyed building and a whole bunch of stuff floated at some velocity. So I'm sorry about that. That sounds pretty horrible. And sometimes I don't always think when I write these tests about, there's a bit of stress involved in throwing a camera up to a hot air balloon that's rising, and I don't want you to feel stressed out either. So on a lighter note, there's a joke. So, what's an impossibly smooth shelf's favorite book genre? Non-friction. I like that. So, there's also this, someone mentioned in the pre-course quiz about the Mid-Autumn Festival, traditional Chinese festival, about getting together, appreciating the full moon and happiness. I hope you enjoy that. This one's out in Markham, but I hope everyone who's celebrating enjoys this. Okay. Also, at the end of last class, I asked you 2 questions. Does friction always slow things down, and can friction ever speed things up? So the answer is no. Kinetic friction of an object on a stationary surface will, convert some of that energy into thermal, and it will reduce the kinetic energy of the sliding object. So it does tend to slow things down. But there's other kinds of friction than kinetic friction. And also, maybe the surface isn't stationary. You can imagine if you're doing that trick where you pull the tablecloth out from underneath all of the dishes. You can imagine that sliding kinetic friction actually speeding up the dishes, right? And they would come flying at you. So sometimes the surface is moving. And I think also, of this truck, if you think of that mass in the back of a truck, could be sitting there. The truck accelerates towards the right. Maybe this mass is also on the truck. Well, what's pushing the mass forward? I think it's the friction, isn't it? That's sticking. And can friction ever speed things up? Yes. So I would argue that it's actually static friction from the floor on my feet which speeds me up as I start running. Because, and the way I think of it is that if it was a super smooth, like non-friction surface, then I wouldn't, I'd just fall down, right? I wouldn't be able to accelerate my entire self. So I think the friction's got to be the external force which is accelerating me. So muscles in my legs push backward on the floor. That's my force on the floor. Then there is an equal and opposite force from the floor on me, which accelerates me forward. And in both cases, it's static friction, I think. So why does friction exist? I think it's because on a microscopic level, nothing is smooth. So if you had a perfectly smooth shelf or something, it would be non-friction. But the rough edges, I kind of think sometimes of all these little, maybe stalactites from the upper surface colliding with the stalagmites or whatever on the bottom surface as the whole thing is trying to move sideways. And it's those collisions, it's probably actually the normal force, really, on a microscopic level of those imperfections on the surfaces hitting each other. And we just call it friction. And the way the textbook goes through is they start with friction when things aren't sliding, and then they go to sliding friction. So I'm going to just reverse that because I like to start with the easy things and then go to the kind of harder concepts. And I find that this sliding kinetic friction is a pretty easy concept to work with. It's intuitive, and I get it. There's a nice little equation. And when we get into static friction, that's when I always get a little confused. And so, and I have to really think a little harder. So let's wait a little bit before we get into static friction. Let's talk a bit about kinetic friction. So the symbol is this whole business with F, K, S on O. There's a lot of subscripts there. But the K stands for kinetic, and then the S and the O are the two surfaces. So, are you doing all right? You got an object, which is the sled, and you got a surface, which is the snow. So there's sliding friction, same thing as kinetic friction. I kind of use the same word here. What it does is when two flat surfaces are in contact and sliding relative to one another, heat is created. So if you had an infrared camera on the snow, you'd be able to see it start to heat up a bit, temperature going up. And you can try to predict it, and there's lots of people who have tried to measure this, mostly engineers, and what they've found is that from experiments, I don't actually know why this is true, but experiments show that you can predict the kinetic friction force by looking at the normal force. So N is the magnitude of the normal force of the surface on the object, where normal means perpendicular, I guess. And then this mu here, this is a dimensionless constant that these engineers would then measure. And you can find tables of what's called the coefficient of kinetic friction. So, coefficient of friction. It's usually a number that's between 0 and 1, and when you multiply it times the normal force in newtons, you get what the friction force, kinetic friction force is in newtons. And we did this on the pre-class quiz this morning. You've got a 1 kilogram block sitting on a surface, a horizontal flat wooden table, and it's sliding along. So it's got some V, I guess, that's going towards the right there. And what I would say, if I was to draw a force diagram of it, is that there would be the normal force of the surface on the block. You've got the gravity force of the Earth on the block, which is the mass of the block times mg, times g. And then, since it's sliding to the right, there will be a kinetic friction force to the left of the surface on the block. And just to check, all three forces I've drawn on my force diagram are on the block, because I'm doing a force diagram of the block. But if we define y to be up and x to be to the right, then since the acceleration in the y direction equals 0, this means that the sum of all the forces in the y direction is equal to 0. So this normal force, I'll just call it n, minus mbg equals 0. And that means that the normal force is equal to mbg. And so Fk is equal to mu sub k times n, which is mu sub k times mbg. So it's going to be the 0.2 times the 1.0 times the 9.8, and you get 2.0 newtons is the kinetic friction force. It's pretty straightforward. So now we have two forces for which there's a good equation. There's gravity, it's always mg, and there's kinetic friction, which is always mu times the normal force. And then we have all those other forces that don't have a good equation for them, such as normal force and tension and this next one, static friction. Do you want to do a top hat? This should show up on your telephone or your device. Here we have a wooden block. I'm going to call that little b, I guess. Has a mass of 10.2 kilograms, so the downward force of gravity from the Earth on it is 100 newtons. The block is sitting on a surface S. Coefficient of kinetic friction between the block and the surface is 0.1. There's no units for that, since it's a dimensionless constant. And you've got a 5 Newton horizontal force applied to the block, pushing it towards the right. And at this instant of time, the block is sliding to the right at a speed of 5 meters per second. So what's the force of kinetic friction of the surface on the block, including the direction? And I'll let you discuss that. I think what I'll do is give you 2 minutes to kind of think, pair, share. You might not use all of these numbers. Should we? You guys able to? 40 seconds? We'll give another 15 seconds. Like 40 seconds? Okay. Ten seconds. Okay. Survey says a lot of people are saying 10 newtons to the left, B. That is the answer also I like. Second most popular answer was 5 newtons to the left. So it doesn't actually matter what was being pushed with. I think what's going on is that you've got that the normal force is going to be 100 newtons. And F sub k is just equal to mu sub k times the normal force. So if you look at the force diagram here, you've got N going up, you've got mg going down, you've got the force of, I guess, your hand or something like that. Hand, maybe, on the B block. And then you've got this backward force of friction, which is going opposite the velocity of the object. Okay? And so I would just say, I'll just use this equation and just find that F sub k is equal to 0.1 times 100 newtons. And you get 10 newtons, and it's to the left because it opposes the velocity. So a follow-up question might be, at this instant of time, is the block accelerating, and if so, what is its acceleration? So once again, let's just draw this. Let's say the force here now is the 5 newtons. We know that. And this is mg. This is, so these two vertical forces do cancel. A sub y is equal to 100 minus 100 over 10.2 kilograms. Anyway, it's equal to 0. But A sub x is equal to the sum of the forces in the x direction divided by the mass of the block. So it's going to be 5 minus 10. So it is actually slowing down. You get negative 0.49 meters per second squared. So it's possible for the acceleration to be opposite the direction of the velocity. That's called slowing down. So if this thing is going to continue sliding forever, then the person pushing will have to push with more than 5 newtons. But at this instant of time, it is sliding to the right. They're pushing with 5 newtons. The kinetic friction is resisting with 10 newtons, and so the whole thing's going to slow down. Vx is greater than 0. And Ax is less than 0, so the block is slowing down. If the acceleration and the velocity are in opposite directions, that means that the object is slowing down. That may have been what threw some of you off with the 5 newtons thing. So your pushing force does not have to overcome the kinetic friction force. There might be no friction force at all, right? If it's something that's just going along at some velocity, no pushing force, the kinetic friction will slow it down. Okay. Let's do an example. A slippery box of mass 5 kilograms is pulled at a constant velocity by a rope, which makes an angle of 20 degrees above the horizontal. So just sketching that out, let's put a block here. Here's a surface. Here's a rope. And I'll draw that theta is equal to 20 degrees above the horizontal. So the system I'm going to say is the box. And it says it's going at some speed. The coefficient of friction is given. What is the magnitude of the tension force of the box? So I'm going to say constant velocity, ding, 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 that's important. Constant velocity means acceleration is 0, so all of the forces on the system have to sum to be 0. Okay, so that's V is constant. So that means that the acceleration is equal to 0 in all the directions. So what we're going to do here is we're going to balance the forces. And you know that mu sub k is equal to 0.03. That's pretty low. That's why it's called slippery, is because the coefficient of kinetic friction is pretty close to 0. But I guess there's another significant figure there. And what you're trying to find here is the tension of the rope on the block. And so in your simplifying diagram step, I'm going to draw all the forces. Normal force going up. Tension force is on a diagonal there. The mg is going down. And there's a force of friction. Fk is equal to mu sub k times n going backwards. And I'm going to define plus y is up and plus x is towards the right. And so when we do that, the diagonal force, we're going to have to split it up into t sub y and t sub x. Oops. T sub x. This is the hypotenuse is t. The angle theta there is that 20 degrees that we're given. And so I know that t sub y this is going to be t times sine theta, and t sub x is going to be t times cos theta. So hopefully you're getting good at taking vectors and converting them to their x and y components using sine and cos from all the practice. So now we're in the represent mathematically step. The sum of all the forces in the x direction, which equals 0, is going to be t times cosine theta minus mu sub k times n. We'll call that equation 1. And then the sum of all the forces in the y direction, which also has to equal 0 since it's not accelerating, is n going up, plus there's a tension component going up, which is t sine theta, and then gravity goes down. Maybe I should call it mb. And we'll call that equation 2. And so what I want to do here is solve for n in equation 2, I guess. And then I'm going to plug into 1 and solve for t. So I've got two equations, two unknowns. So if you look at equation 2, you can solve it for normal, which is mb times g minus t sine theta. So this is a good little lesson. I think a lot of people, if they do a lot of physics in high school, they sort of memorize that the normal force is equal to mg, and that is not. It's often true. If something's not accelerating and it's on a flat surface and there's no other forces, then the normal force cancels mg and they turn out to be the same. But in this example, you've got a rope attached to it, and it's not accelerating, but some of the force that's supporting the object's coming from the rope, so the normal force is less than mg. Anyway, now that I have this, I can just plug it into equation 1. And so 1 becomes 0 equals t cos theta minus mu sub k times, I'll open a big bracket here, the normal force, which is mbg minus t sine theta. So now the only unknown we have in this equation is t, and we're trying to solve for t. So hopefully you're good at algebra and you can gather terms with t on the left-hand side. So you can solve for it. So there's going to be a negative mu sub k times t times sine theta minus t cos theta. That's all the things that have t in it, and there's only one term that doesn't have a t in it. I'll put it on the right-hand side. Mu sub k, negative mu sub k times mb times g. I guess they're all negative. So I think I can just times both sides by -1, since every term is negative, and make them all positive. So I'll end up with t times cosine theta plus mu sub k sine theta equals mu sub k times m sub b times g. So t is equal to mu sub k times the mass of the block times g divided by cosine theta plus mu sub k sine theta. Not too easy. But now you just plug the numbers in. I would say that t is equal to 0.030 times 5.0 times 9.8 divided by cosine of 20 degrees plus 0.30 times sine of 20 degrees. You have to plug all that into your calculator. I got 1.5174 newtons. So T, I guess you could round it to two significant figures if you want, 1.5 newtons. Okay. And this is a small force. A newton is pretty small. You probably figured that out in practicals. But it's a slippery surface, so that's okay, since mu sub k is low. That's sort of my evaluate step. Oops, sorry. Wrong button. Okay. This is an example of solving a problem, chapter 4 kind of problem, like you might get in the test. So now we're going to move on to static friction, which I find to be a little harder. And let's do a conceptual question first. Static friction is when the surfaces are not sliding. Okay, they're locked together. So basically, if you have two surfaces, they're either sliding, in which case there's kinetic friction, or they're not sliding, in which case it's static friction. You always have one or the other, right? It's friction, but you calculate it in two different ways. So unfortunately, similar to normal and tension, there's no general equation for static friction. It's just whatever is required. It's one of these as-needed forces. So let's do a top hat question on this and see what you think. This one, be careful with this one because there may be more than one answer. And in order to get this correct, you have to, so there's three forces that you can imagine on this green car, which is A, the gravity force on it from the Earth, B, the normal force of the surface on the car, and C, the static friction. And so it's parked on flat horizontal pavement. Which of the three following forces should be drawn on the force diagram so they're non-zero? If it's a 0, you just don't even draw it, and we're not going to click it for this question. Make sense? Please check your neighbor. Make sure your neighbor gets what's going on here. Or that you agree with each other. 30 seconds, I'd like you to click in. Maybe more than one answer. You get points for clicking all the non-zero forces and none of the zero forces. 5 seconds. Okay. Survey says, yeah, so the idea with C is that it's 0 because it's a flat surface. So that's what I was trying to get at there, is that there's no static friction unless it's needed. It's an as-needed force. If the car was parked on a hill and the parking brake was on, there would be some static friction to prevent it from sliding down the hill. And the way I always try to figure out static friction in my head is I imagine, what if this surface was perfectly slippery? Then what would happen? Well, in the case of this green car, nothing would happen. If it was parked on ice, it wouldn't matter. It would still stay there. So no static friction is needed in this case, so you don't even draw it. So it's these ones. And this one's equal to 0. Okay. Want to watch a little video? I'm just going to go through a couple of things from the textbook kind of quickly, just from your reading. But the videos can be a little fun to watch. Measuring the force needed to move a block. So the static friction is canceling out this pulling force all the time. Whoop! And then there's some sort of maximum. And then it starts sliding. And you can sort of see where the maximum is. It looks like, at about 3.2 newtons is when the whole thing starts sliding. So this experiment, if it's like that car, it's just sitting on a horizontal surface, then you've got the normal force canceling gravity with no friction. But if you then apply a force, a spring force, pulling towards the right, then what you say is that this surface force kind of ends up being on a diagonal. And what we do is we define the perpendicular component, the component that's perpendicular to the surface, we call that the normal. And the parallel component, we call that static friction. And they're both kind of self-adjusting, but basically the more she pulls to the right, the more the static friction resists it. And the static friction cancels out her pulling force, and that's what keeps the block stationary. So the more she pulls, the more the static friction force reacts. So in each of the experiments, the surface exerts a force on the block that can be resolved into the perpendicular and parallel. The perpendicular component doesn't change because the pulling force is parallel to the surface. So the magnitude of the parallel component can only increase up to a certain value, and then the thing starts sliding. So that's where this experiment on static friction comes in. So there it is. There's static friction. There's normal. The component of the force of the surface that's perpendicular, we call that normal. And the component that's parallel, we call that static friction. I always draw these as separate arrows on my force diagrams, just because I don't want to draw a diagonal thing. I don't like diagonals. It's easier to just draw N and draw F and kind of imagine they're two separate forces. You did it on your pre-class quiz. There was a packing crate sitting at rest on an inclined loading ramp, like this. There's a crate, I guess. And how does the magnitude of the static friction force component of the force exerted on the ramp on the crate compare to the other forces? And so the way I would do this is I would say you've got normal, and then you've got static friction, which is holding it from sliding, and you've got mg down here. And so the way that then I do it is I tend to tilt my axes. So I've got x this way and y this way. I define my axes as tilted so that mg becomes a diagonal force where you've got fg, negative fgx and negative fgy with this coordinate system. And this angle theta, you can kind of figure out from geometry, turns out to be the same as this angle theta in the force. And then what happens is that you've got the sum of the forces in the x direction equals 0. That's going to equal to the static friction minus the mg times sine theta, I think. And so the static friction force is just mg sine theta. It's the component of the force that Earth exerts on the crate parallel to the inclined ramp. That's what That's what static friction does. So 99% of you got that one, that's great. Let's do top hat, I think. Question? So now, it's a bit similar to the previous one, but now the block is not moving. So there's no sliding. This is a static friction problem. Wooden block has the same mass. There's a normal gravity force of 100 newtons pulling it downwards. And the coefficient of static friction, mu sub s, between the wood and the concrete is 0.2, which I think is bigger than the mu sub k was when it was sliding. We'll talk about that in a bit. Now, same thing, a 5 Newton horizontal force is applied to the block, pushing it towards the right, but the block does not move. What is the force of static friction of the surface on the block? So think about this. Check your neighbor. Make sure you and your neighbor want to vote the same way. Some people have asked me, how do you do well in physics? And there were two main resources I had when I was a student, which was my textbook and my friends. And I kind of alternate back and forth. And I mentioned that static friction was always a tricky concept for me. And I found it was really helpful to try to discuss these things with my friends. The idea here being, I like it, C, which is it's just as needed. So what's needed to keep that thing from sliding? Well, I'm pushing it to the right, so it wants to slide to the right, but it's not. So why not? Because the static friction just has to cancel out whatever I'm pushing with. I stop pushing, there's no static friction needed. If I push it with 5 newtons, then static friction has to be 5 newtons. So there's no equation, but there is an equation, so let's try to talk about that. All right, this gets a little weird, so let's look at these videos. How does the surface affect the friction force? So what they're doing is they're measuring the maximum friction force when it slides on a mirror, measuring it again when it slides on some other rubber surface, and measuring when it's on a table. So the force that gets it going changes depending on the different surfaces, and also how much mass is resting on top of it. Oh, I see. She's trying different orientations. In this case, it didn't matter. It was always about 4. How does mass? Yeah, so at this point, I think she stacks different masses, but leaves the table the same. And it turned out that the maximum force needed to get it going was bigger the more things were stacked on top. So it goes up. So let me summarize what was going on in those videos. First experimental result was, so the maximum static friction force is when it just starts sliding. You've kind of gone beyond something. And that increased when you changed the surface from a table to a mirror to rubber, or changed. So there's different coefficients of static friction. Experimental result 2 was that different amounts of surface area between the wood and the table didn't matter. Surface area doesn't seem to matter. Same amount of maximum friction. And then experiment 3 was that when she stacked more things on top of the wooden block, it got different, for sure. And then at some point, I think they did a test to see, well, is it the mass or is it the normal force? So what they got is a tiny little skateboard and pressed it down with some force. So not pressing it gives some maximum static friction. Pressing the tiny skateboard increases the static friction. So it's not the mass of the object that matters here. Now I think it's the normal force. So there you go. Keeps on going up the more you press down on the tiny skateboard. So this is pretty clever. Maximum static friction force, the more the skateboard pressed down. So we conclude it's the normal force which produces more maximum static friction force. We're okay. Okay, so basically, let's sum up. There's a limit to how big the static friction force can get. If you push hard enough, then the object will slip and start to move. So, I mean, I said it's as needed, but now there's a maximum, so it's kind of interesting. I guess there's probably a maximum tension force, or else the string would break, or a maximum normal force, or maybe you'd go through the floor if there was an elephant on the table or something, you could break it, right? So this is kind of like that. What's the maximum static friction before then things do start accelerating? A static friction force greater than Fs max is not possible. Okay. So, and then there's an equation for the maximum. This gets a little confusing. It looks exactly like the equation for kinetic friction. But now it's not the equation for static friction, it's an equation for the maximum static friction. And mu sub s is now called the coefficient of static friction. So there was a pre-class survey this morning, and there were some questions about friction, so I just want to go over them really quickly. Somebody asked, how can normal mean the same thing as perpendicular? Good question. There is a difference. I think normal means perpendicular to a plane, and perpendicular means perpendicular to a line. I think it's just the difference between 3D and 2D. If you're thinking of everything in 2D, then yeah, normal and perpendicular simply mean the same thing. But think of a normal force, it's normal to a surface, which is a plane, right? Slightly different. How can you differentiate between static friction and kinetic friction acting on an object? Is it contingent upon the object's state of motion? And that's exactly right. Okay? Only one kind of friction force can act on an object by a surface at any moment of time. It's either static or kinetic. We call it static friction if the surfaces are kind of locked together, okay? And if they're bumping along each other, we call that kinetic friction. It's always parallel to the surface, and I guess perpendicular to the normal force, and it's because of those imperfections. And then there was this question, how does on the pre-class quiz, how does the coefficient of static friction compare to the coefficient of kinetic friction? The coefficient of static friction is generally greater than the coefficient of kinetic friction. So this is a table from your textbook, but it comes from measurements done by engineers of various different surfaces. And it's interesting that rubber on concrete, dry concrete, can actually get up to a coefficient of static friction of 1, but the coefficient of kinetic friction is less. And it's always less if you look at these tables. And sometimes it varies depending on the different materials. There's a plus or minus, I guess, in some of these ranges. Wood on wood. It gets less and less for slippery things. Teflon. Those look about the same, actually. Teflon has the same coefficient of static friction as kinetic friction. But once again, there's no real fundamental physics in all of this stuff. These are just measurements and approximate relations. And this whole friction force is mu times the normal force is sort of an approximate relation. Actually, what I want to do, I think I have a bit more time. Let's do one quick top hat question for you. Same wooden block, exactly the same thing, and same coefficient of static friction. Now, what is the maximum horizontal force that you can push on this and have it still stay still? And this is a typical kind of question you're going to get on tests. They say, what if it's just about to slip? And now you're going to use that F sub thingy, right? Fs comma max is mu sub s times the normal force. So okay? I'll let you guys work on that. I hope you have a great weekend. Keep going with Chapter 4. We'll continue on that on Monday. Have a good one.